Okay, so welcome everyone to this particular video where we continue looking at questions on Kirchhoff's laws on electric circuits, specifically on Kirchhoff's laws. So we have question 1, which is saying the currents are steady in a circuit of figure 4. Find current 1, 2, 3, 4, and 5, and the charge on the capacitor. Find the current 1, 2, 3, 4, and 5, and the charge on the capacitor. So this is the circuit that we've been given, and the first thing we're going to do first is redraw this diagram into a more friendly form in case this is a bit ambiguous. Let's just put it in a straight, simple form, which will be easier for our analysis. So I'm going to draw it straight. I have a line here at the top. I have a resistor there, which is having a magnitude of 3.0 ohms. I have battery voltage there, which is having a magnitude of 9.0 volts. Okay. I have a vertical line there. I have another battery voltage there, which is having a magnitude of 8.0 volts. 8.0 volts. I have another resistor here, which is having a magnitude of 4.0 ohms. And what else do I have? I have another diagonal loop. Okay, so I have a resistor here, or rather battery voltage. I have battery voltage here. Let me just reduce the size of it. Okay. I have battery voltage, the negative terminal and the positive terminal there. Then I have a capacitor. This capacitor is labeled F and G on the plates. Then I have a resistor there of magnitude 2.0 ohms, like this, FG. Okay, this is the longer plate. This is the shorter plate. I have a FG here on the resistor, which has magnitude 5.0 microfarads. 5.0 microfarads. Then I have current. Just change the color. Okay, we'll do this. So we have current 2 directed in this direction. We have current 1 directed in this particular direction. We have current 4. Current 4 there. We have current 5 in this particular direction. And what else? Where is our current 3? We just counter check. Current 3. Okay, current 3 is here. Current 3 is right there. Then I have my junctions A, B, C, D, and E there. I guess that is all we have on the diagram. Let's just check it again. Okay, current 4, A, B, C, current 2. Okay, I've forgotten the magnitude of this particular resistor. Okay, this is 7, or rather the battery voltage. This is 7.0 volts. 7.0 volts on this battery voltage. And I guess that is all we have in this particular diagram. So from this diagram now, we can start solving for the missing currents that we've been told to find. And the first thing we're going to notice is that we're going to notice something that we have a part where we've been given a capacitor on this loop here where we have the current 5, or I5, or DC, from point D to point C. We have been given to say there's a capacitor, and that's where we are given that there is current 5 passing through. So what we're supposed to know is that if a capacitor is fully charged, it basically acts as an open circuit. So in this case, what are we going to notice? We're going to say if this capacitor, FG, these two plates, FG, that are going to inhibit the flow of electrons are fully charged, they are not going to allow any current to pass through them. What does that mean? That means automatically the current that is passing through this point D to C is going to be equal to 0 because there's a capacitor that is fully charged. So there automatically we have already found what current number 5 is. So I'm going to say I5 is equal to what? It's equal to 0 amps. I5 is equal to 0 amps. Why? It's because it's passing through a fully charged capacitor, which is going to act as an insulator. It is going to break the flow of electrons, hence acting as an open circuit. So I5 is going to be equal to 0 amps. I5 will be equal to 0 amps. Hence, we have calculated one of the answers that we have, or that we've been asked to calculate. The next thing we can do is now go to the next loop, for which I'm going to choose the loop ACBA. Where is ACBA? We have A, C, B, back to A. So if I choose this loop, that means already I have directed my loop into an anti-clockwise direction. And if I'm choosing this way, I'm going to apply the Kirchhoff's voltage law, which is to say the summation of the voltages across a closed loop shall be equal to 0. So what am I going to say? I'm going to say from point A to C, what do we have? We have battery voltage. If I'm moving in this particular direction and the current is moving in this particular direction, then what are we going to notice here? We have or we are flowing from the positive plate to a negative plate. We're moving from this positive longer plate there to a negative plate. That means we're having a voltage drop. So this is going to be equal to minus 8V, which means minus 8. Then from point C to point A, we don't have anything. We just have current 2. Then from B to A, we have this particular resistor, and there is voltage passing through this particular resistor. What voltage is that? We can see to say current or current 2 is flowing through this direction. So what does that mean? That means the voltage across this is against the direction of current. So that is a voltage gain. So that will be plus 4I2. And this is going to be equal to what? This is going to be equal to 0. That is an equation that we're going to get from the loop ACBA. So from here, you can tell, say directly, I can calculate my value of 2A, or rather current 2, because I'm going to have 4I2 being equal to 80. Then I divide both sides by 4. That means the current 2 is equal to 2.0 amps. Current 2 is equal to 2.0 amps. I can even write it here on the corner. Current 2 is equal to 2.0 amps, just like that. The keyword is noticing the direction or the directing the loop in the way we've directed it. I've directed it in an anti-clockwise direction. So that means from point A to C, our direction is flowing from the positive plate to a negative plate. That means there's a voltage drop. So it's a minus 8.0. Then from point B to A, we have a current 2, which is flowing against the direction of the loop that we've chosen. So that is going to be a voltage gain, because the voltage that is passing through this 4 ohms resistor is against the direction of the current. So that is the voltage gain. So I'm having my positive 4I2 there. Then if we manipulate that equation, we're going to get current 2 being equal to 2.0 amps. We can go to our next loop. Of which the next loop we're going to look at is ADECA. ADECA. This is A. We just use this guy. So we're going to for A, D, E, C, and D back to A. So what are we going to notice on this particular loop? We're going to notice to say we have this resistor here, the 3 ohms resistor, and we have current that is passing through this this particular resistor as current 1. Current that is passing through this particular resistor is current 1. So let me just rub here. You can tell to say the direction of the loop that I've given is anti-clockwise as usual. And the current one is also directed in this same direction. So this is I1. So the voltage that is passing through this particular resistor is along the direction of current. That means we're going to have a voltage drop on this particular point. So what am I going to have? I'm going to have minus 3I1. That is a voltage drop because the voltage passing through this particular resistor is in the same direction as the current. So I'm going to have minus 3I1. Then I'm going to have then we go to point EC. From point E to C there, we have current passing through in that particular direction, and we're moving from a positive plate to a negative plate. That means we also have a voltage drop from this particular battery voltage here. So we're going to have minus 9. Then we go to point C to A, where we have current moving in that particular direction, and we're moving from the negative terminal to the positive terminal. So we have a voltage gain. So I'm having my plus 8 there. This was going to be equal to 0. Then we can solve this equation to calculate the current I1. So we're going to have our negative 3I, I1 being equal to minus 9 plus 8. This is minus 1. This is going to give us 1 over minus 3, even here over minus 3. Therefore, our current 1 will be equal to negative 0.33 amps. Negative 0.33 amps. So I'm also going to write this one here on the corner. I1 will be equal to negative 0.33 amps, like that. Okay. So we've solved for the third one. We're now remaining with 2. We've solved for the third one. We're remaining with 2 currents. We can go to the next loop. And go to the next loop, of which the loop that we're going to go to now is uh or we can now apply Kirchhoff's current law, junction rule at point C. Yes, so let's apply Kirchhoff's current law at Kirchhoff's current rule at point C. So in order to say the Kirchhoff's current law states to say the sum of the currents that are entering a particular junction should be equal to the currents that are exiting that same junction. So if I make C my junction here, I'm going to notice to say there's current 1 that is entering junction C. There's current 2 that is entering junction C. Then there's current 3 that is leaving this particular junction. Or we can also include current 5 since it's also entering this particular junction. It's moving in this particular direction. Even if it's equal to 0, we can include it to standardize our calculations. We have current 5, current 1, current 2 entering junction C. Then we have current 3 that is leaving this particular junction. So we're going to say I1 plus I2 plus I5, this should be equal to current 3. That means we have justified Kirchhoff's current law. The sum of the currents that are entering junction C should be equal to the sum of the currents that are leaving junction C. So what is current 1? Current 1 is negative 0.33 amps plus what is current 2? Current 2 is 2.0 amps. And what is current 5? Current 5 is 0 amps. And this should be equal to current 3. This should be equal to current 3. That means the current 3, let me just rub at the top here. That means current 3 will be equal to minus 0.33 minus 0.33 plus 2. Current 3 will be equal to minus 0.33 plus 2, which is going to give us 1.67 amps. 1.67 amps. So current 3 is equal to 1.67 amps. I can write it on the corner too. Say current 3 is equal to 1.67 amps. Just here. Then which other one is remaining? We are now remaining with current 4, of which for us to calculate current 4, we are also going to apply Kirchhoff's junction rule at point A. Going to apply Kirchhoff's junction rule at point A. So that is how simple questions on Kirchhoff's law are. You just have to understand and master the rules on how to direct a loop and what you're going to follow in directing a particular, or when you have directed a particular loop. When you are crossing over a battery voltage, are you going to have a voltage rise? Are you going to have a voltage drop based on whether you're moving from a positive to a negative terminal or a negative to a positive terminal? So current at point A, if we apply Kirchhoff's current law, we're also going to say the same. Current entering a particular junction should be equal to current leaving that particular junction. So if you look at point A, what do we have? We have current 3 that is entering this junction. We have current 3 entering junction A. Then we have current 4 here leaving that particular junction. Then what else do we have? We also have this current 2, which is pointing in this direction, which means it's leaving this junction. So current 3 is entering, whilst current 4 and 2 are leaving the junction. So we're going to say current 3 is equal to current 4 plus current 2. And this is going to give us what? Just going to use the values that we already have. We're going to say current 4 is equal to current 3 minus current 2. That means our current 4 is equal to current 3, which is negative, or which is 1.67 minus 2.0. This is going to give us negative 0.33 amps. So current 4 is equal to negative 3. Current 4 is equal to negative 0.33 amps. So that is current 4 like that. And we can now move on to the last question. We can now move on to the last question, or rather the last part of the question, which is saying we should find the charge on the capacitor. We should find the charge on the capacitor. So to find this one, we'll apply the Kirchhoff's loop rule in the loop where we have the capacitor itself. So I've chosen this one. We'll go with D. We'll go with D, C, E, D. Move from this point, D. Move from D, C, E, and back to D, where we have Fg as the capacitor itself. So to find voltage across the capacitor, or the charge on the or the voltage across the capacitor, we're going to apply the loop rule on this particular loop that I've just shown you, D, C, E. Since we have F and G across this loop, we can just say DFG, CE, D. It's one and the same thing. So I'm going to say I have my current 5 passing through the 2 ohms capacitor or the 2 ohms resistor along the direction of current. So we're going to have a voltage drop of minus 2I5. Then we are going to have voltage on the capacitor. So I'll say plus V on the capacitor, which I'll just name it FG. Then we're going to have a voltage drop on the battery capacitor, since we're moving on the battery voltage, since we're moving from the positive terminal to the negative terminal. Sorry for that. I'm moving from the positive terminal to the negative terminal, so that will be a voltage drop. So I'm going to say -7. Then we'll go in this particular direction. We're moving from the positive terminal to the negative terminal on the battery voltage. So that will be a voltage gain, or voltage rise. So I have my +9 there. Then on the 3 ohms resistor, we are moving in the opposite direction as the current I1. So that will be also a voltage gain on the 3 ohms resistor, this particular point. So I have +3I1 like this, and this should be equal to 0. We can now close the loop. We can now close our loop. Then from here, we can calculate the value of V final or VFG. We'll have our V on the capacitor being equal to, I have 2I5, and this is basically 0 since I5 is 0. So I have -7 plus 9, which is going to give me 2 plus 3I1. And you know, to say 3I1 is minus 0.33. Yes, minus 0.33. So I'm going to have -2 minus 3I1 is negative 0.33. I guess this is the correct way we're supposed to write it. Okay, yes, I1 is negative 0.33. Then if I move this to the other side, it becomes negative. Even here, I'm finding a +2. If I take it to the other side, it will be negative. Okay, so that's that. That means my voltage across the capacitor should be equal to, let me just plug this in. Let me just plug this in into my calculator. This will give us, this is going to give us -1 volts. Let me just change again. Negative, why can't I write? Okay, -1 volts like this. And we know to say, from here now, we know to say, to calculate the charge on a capacitor, we use the formula Q is equal to CV, where C is the magnitude of capacitance and V is the voltage across that particular capacitor. So we'll say it's Q is equal to CV, and therefore we're going to say our Q will be equal to the magnitude of the capacitance, which is 5 microcoulombs or microfarads, multiplied by the voltage. And which voltage are we going to use? We're going to use the voltage that we've calculated, 1. And therefore, Q will be equal to 5 microcoulombs, 5.0 microcoulombs. And just like that, ladies and gentlemen, we are done with question 1. Just like that, we are done with question 1. We can now move on to question 2.